a presentation. So I will start with the first speaker, Svitlana Sovinska. She will talk about the synthesis and characterization of pure and Ag-doped zinc selenide for nanowires for PV applications. So we have 15 minutes, and after we come back to the questions. Oh, yes.
Today I will be present about some part of my work. It's about the synthesis of zinc selenide and zinc selenide doped with silver nanowires for photovoltaics. As the first, I short introduction. As we know, there are three generations of solar cells. The first generation is silicon cells. The second generation is thin film technology of solar cells. It's a monolayer of cadmium telluride and CEGS and ZnSe. But the problem of this solar cell is this cell is very costly, and today the science provides many investigation for new materials for solar cells. And the third generation of solar cell, we have, for example, many solar cell based of typical PN junction, of non-typical PN junction. For example, it's a mixed polymers, conductive polymers with nanoparticle or organic solar cell. The advantages of this hybrid organic inorganic and organic solar cell is that these materials may be printed in our, for example, clothes in different materials. What about the hybrid organic inorganic solar cell? In the figure 1, I present the typical device structure of this solar cell. This solar cell consists of two electrodes. It's ITO and aluminium, and the active layer is a conductive polymer and zinc selenide, for example, nanocrystal in this case. The energy level diagram, I'm so sorry. Okay. Okay, in the typical diagram, we have the trace separation between polymer and our nanoparticles. For example, from LUMO, from conductive polymers, the electron moved into the conductive gap on zinc selenide, and the whole move into the valence gap from HOMO in this polymer. Most important that, for example, in science, in literature describes that the most efficiently solar cell based on one-dimensional nanowires and zero-dimensional mixed with polymer. And today we'll be present about the one-dimensional nanoparticles and this synthesis. In the figure 3, we have the ideal electron configuration for solar cell based on conductive polymer. As conductive polymer, we used, for example, P3HT, for example, P7, and inorganic nanoparticles. As we can see, the electron and hole move into the polymer and from inorganic nanoparticles to polymer. And in this case, we need good percolation for high efficiency of this solar cell. The working principle of hybrid solar cell is that after the absorption of of sunlight, we have the generation of exciton in the donor materials, and then we have the diffusion of this exciton to the donor-acceptor interface, and the dissociation of exciton and change separation. And after we have the transport of hole and electrons to respective electrodes. And in a typical synthesis for zinc selenide and zinc selenide doped with silver nanocrystals, we used the hot injection method of synthesis, and in the typical procedure we used two precursors. It's scheme for zinc selenide nanocrystals, In the one flag we have the octadecilamine and selenoura, and the second precursor was the octadecilamine and zinc stearate. After the dissolving of this selenoura and zinc stearate, we have a hot injection of these precursors, and next the synthesis. Synthesis will provide 1 hour, and then we have the purification and centrifugation and drying of our nanoparticles. In the case of zinc selenide doped with silver nanoparticles, we use 2 methods of synthesis. The first method when we have the 2 precursors. The first one selenium precursors, and the second was zinc and silver precursors in one flag with octadecilamine, and the method 2 was 3 precursors. The first was selenium, zinc and silver precursors in the different flags. For example, we have many different syntheses, the different molar rate of zinc to selenium and silver. And for example, in the figure 6 and 7 presents the TEM image of zinc selenide nanowires without silver. As we can see, the length of this nanocrystal is about 8 for 10 nanometers, and the diameter is about 2 or 3 nanometers. The next, when we have the zinc selenide doped with silver and nanoparticles, we have in the molar rate of zinc to silver 50 to 1, we have the 2 phase of nanocrystals. It's zinc selenide doped with silver, and the second phase was zinc silver selenide nanoparticles. But the next synthesis was synthesis of zinc selenide doped with silver. It's figure 10, but this synthesis was provided from method 2. In the figure 11 we have the zinc selenide nanowires, but the molar rate of zinc to silver was 100 to 1. And we can see this is zinc selenide doped silver nanoparticles without the added of zinc of silver selenide phase. And we can see the addition of silver and the molar rate of zinc to selenium. In this case, we have many different nanocrystals, and these nanocrystals have different optical properties. And the next, I have present the sample 8.5. This synthesis, the molar rate of zinc to selenium to silver is zinc to selenium is 1 to 1, and we can see we have the heterostructures in the band of silver selenide. And in the next we have the addition of silver to 30 to 5 to 2, and we have these nanocrystals are smaller than in the first example. And we have the next synthesis, for example, is zinc, molar rate of zinc to selenium is 2 to 1, and we can see the additional of phase of zinc. And for typical solar cell, we used zinc selenide nanoparticles and PAS3HT polymers. As you can see in the figure 25, it's polymers under illumination and in the typical photovoltaic cells. For example, in the figure 22, we have the voltage current characterization for these devices, and the efficiency of these devices is about 1. But the problem of these devices is that the zinc selenide nanoparticles have in this surface octadecilamine. And in next step, we have we have made a surface modification of these nanoparticles and maybe do this solar cell. And as conclusion, the results show the octadecilamide is an effective coordinating solvent, and we use octadecilamide as a coordinating solvent and stabilizing of other nanoparticles. For example, in literature, describe for synthesis of one-dimensional nanoparticles uses of two solvent, for example, of two coordinating compound. And amount of used precursors and order of their addition in the synthesis allow to obtain nanocrystals with different structure and properties. And for next fabrication for our fabrication of photovoltaic cells, with the use of zinc selenide and silk selenide open with silver nanocrystals requires modification of their surface to provide the high efficiency of these solar cells. And thank you for your attention.
Thank you. So we have some questions, please. Any question, please? Yes, please. You always ask questions. This is good.
When you show us those long wires with another particles attached to it, can you show it again?
Oh, shift. Okay.
Oops.
It's
This one, yeah. You mentioned that you have the spheres of silver selenide and wires of
zinc selenide with silver.
So, get the point, but you used those structures to build your solar cell or not?
Yes, we have, but in this presentation I have not, but I know that this nanowires is zinc selenide doped with silver, because, for example, we have the spectrum of silver selenide and pure zinc selenide nanoparticles.
And can you again remind me what was the reason of silver doping?
The absorption of these nanoparticles is higher than in the pure zinc selenide.
I think I want to clarify something here, because as you can see here, these silver nanoparticles or nanocrystal, if we say doping, that means they are dissolved in the crystal structure.
But there is another story.
Because the color, it shows that silver particles are separate.
Not silver, silver selenide.
No, Ag. This is the chemical contrast for chemical analysis, no?
But you
It is.
Yeah.
But you don't have selenide signals there, so you don't know if there is a selenide.
No. The spots are very clear in red. That means it's a silver. So because I did also on thin film, it's difficult to incorporate silver in thin films, or in silver. It's very complex because I always get nanocrystals of silver separately. So the word doping, it's different than monodispersed. Any question, please? Yes, please.
What was the efficiency of your cells and how much is it improved in comparison with the initial structure without your polymer?
Pure. Between pure and after doping.
I have in this presentation zinc
Yes,
selenide, yes.
this one.
But in this, the problem of this solar cell is that the zinc selenide have on the surface octadecilamide, yes, and we need to the new method of purification of these nanoparticles. And for example, we have the modification of zinc selenide nanoparticles with conductive organic particles, and in this case we have the efficiency 1.8. But for zinc selenide doped with silver, the efficiency is 1.9 or 2%.
Have you done any optical properties to show the difference sometimes?
No, in this presentation.
UV absorption. Any question, please? Okay, thank you so much. Let's applaud our speaker.